So let's start with NOCs, right? And so on-chip networks, of course, have become very popular, especially with the whole many-core era, right? And so the current top 500 supercomputer, which is the Tiahue Lite, has 260 cores, and of course, an on-chip network connecting them, though we don't know a lot of the details. IBM's True North chip, which is a neuromorphic chip, had 4,096 cores, and there's a lot of 1,000 cores prototypes for the exascale system, and people are also talking about alternate technologies for the on-chip network. So this is kind of where the on-chip network fits in. This is similar to what Jason presented. Essentially, you have a bunch of controllers on chip. You might have a set of L1 controllers, you might have L2 controllers, or these could be L3 controllers depending on the system. And the on-chip network is what connects them, right? And it could basically just be a bus, or it could be something more complex depending on scalability. So what kind of traffic goes on this network is what Garnet essentially models. So as a very simple example, let's say I have a piece of data sitting at that core, that's A, and this core has a load request. So then in the network, after you go through the various layers of translations, essentially there's going to be a request packet that gets sent out to, let's say, an L2, which might be the home node. The L2 generates a forward packet, sends it to this core, and this actually sends the data cache line response to A, right? So essentially you have 3 hops in the network to deliver this piece of data. And so this has implications on how much performance you're going to get, especially if the data is on chip. If you're going off chip, yeah, of course, you might be more memory limited, right? So this is what modern NOCs essentially look like. A tile system. You have each tile has a core, an L1, an L2, maybe a slice of a directory or an L3, and a network interface that connects to a router. The network interface is what converts these cache messages into packets that get into the network. And within the network, depending on the bandwidth of each link, packets get broken down into what are known as flits. Okay, so now at a very high level, a network consists of these 4 components. You have the topology, which is essentially analogous to how you would build road networks. So I'm going to use this analogy just to explain the 4 concepts. So if I have a 4 set of nodes, how I lay down my roads is essentially the topology. Once I have the topology, routing decides which exact path I take. And so here I might have 2 paths to get from that node to the other, and both of those are valid routes. And in some cases, I might be going more hops, but as we've often seen when we are driving, that might actually turn out to be faster just because of congestion. So that's routing. Once you fix the route, flow control is what decides when you get to use a particular link. Because fundamentally, we are sharing links here. We don't have enough bandwidth, enough real estate to just have all-to-all wires. So these are analogous to traffic signals. Like once I've decided my route, if there's 2 flows, which one actually gets to use it at a particular point of time. And finally, the microarchitecture is what decides the exact implementation of those intersections. How many lanes I have, maybe I have a stop sign, and so on. That's the analogy of these 4 components. Okay, so now, so that's like at a very high level what a network is. As I said, so your topology, routing, flow control, and microarchitecture, and we'll jump into those when we go into Garnet. So why do we care about NOCs, and why should we model them accurately? So I'll give a brief glimpse by 2 case studies. Both of these were done with Gem5. The first is a case study where we compare directory and broadcast protocols. And so again, intuitively, we know that broadcast protocols are harder to scale because they have a lot of traffic requirements and bandwidth requirements from the network. Directory protocols are easier to scale, but then they add storage overheads. So in this slide, what we've done is just an average across a suite of parsec workloads, 64 cores, and this is just normalized full system runtime. And the idea is, on the leftmost side, we see that as we saw intuitively, the broadcast-based protocols, these are the AMD Hammer protocol and CMP token, they have worse performance compared to a baseline just because the NOC is a very traditional NOC. But once I start looking at more clever NOCs, I can actually reach designs where I can have broadcast protocols that have comparable performance and sometimes even better, right? So the way you implement your network can actually have implications on how your overall system performs. Similarly, private versus shared caches is a very classic debate. Private caches are great. They are local, so I can access them fast, but they cause replication. Shared caches are bad because I have to go far away on the chip. But again, if I have a network that lets me go that distance very easily and quickly, again, I might have scenarios where a shared cache actually performs very close to a private cache and at the same time gives me benefits of no replication. So the point I wanted to make is different NOC microarchitectures may lead to different microarchitectural decisions and open new design optimization opportunities. And this is what Garnet aims to enable. So just a brief history about Garnet. So this is currently part of the Ruby memory system. It's not part of the classic memory system. The original version that was in GEMS was a 5-stage pipeline, which was released in 2009. And that was developed by Niket, who's at Google right now. And the new version was released last year. And these are just some resources. And I also have, when I teach my OnChip Network course, I actually use Garnet as the research tool for labs. And so I have some of those on the website that I've listed there in case somebody wants to get started using them. Okay, so now, as I said, right, the first component is topology. So how do I connect my various components together? And so Jason alluded to this. Essentially, these are all of the controllers that my protocol will describe. And let's say I have all of these. And so the topology is the way I connect them. And so in Garnet, or in, I guess, Ruby's network model, what you do is you first start by instantiating routers that you connect to these controllers externally. So let's say I have these 6 routers that I instantiate, and I use external links to connect to these external controllers. And these are bidirectional links by default in the code. So you have to just instantiate it once. And maybe what I do is I say that, okay, all of those controllers get connected to that router, all of these connected to this, and so on. And of course, there's an inherent assumption here. This is kind of a co-design of the protocol and the topology. So the protocol designer maybe has assumed that, that L2 is like a home node for the network and it's shared. So there's certain assumptions because of which these controllers exist, and this is how we connect them externally. And now internally, I can connect them up by any topology I want. And I could have all of these connected to one router and just make it into a big crossbar. I could have all the routers connected with all-to-all links, making it the point-to-point topology Jason presented, or I could have a mesh. So now we instantiate internal links to connect these. And so as an example, these are unidirectional in the topologies in Garnet. So you have a link that connects this router to this, and so on. So from west to east, east to west, south to north, and north to south. So what we've created is a mesh topology. And this is actually the mesh dire corners the topology file in the code base right now. I'll mention why we have the XY there. And so what you notice is there's 4 directories in the system, 4 memory controllers, which we've connected to the corners through these external links, and internally it is a mesh, right? So now you have configurable parameters in the topology. One of the configuration parameters is just the router latency. You can actually specify what latency you want. So we do allow you to have heterogeneous routers where some routers have more latencies and some have less. And that's intuitive because some of them might be higher radix with more ports, some of them might have fewer ports. So this is something you can specify in the topology file, or you just use the defaults. At the link level, you can specify what your link latency is in cycles. Again, this can be set per link individually, or this could be something that's a default parameter. You specify link weights, and this is used to bias your routing algorithm that I'll talk about in the next slide. You have link or port directions that you can set. These are just strings. You can say that, I have this port is an east port, this port is a west port. And again, these are more for just readability. When you finally print out your config, it tells you what port is what. This only, of course, helps if it's a regular topology. If I have some crazy topology, you may want, some internal names you come up with just for that readability. And it also lets you, if you really want to customize, have some very fancy routing algorithm, it lets you do that. So that's something you can specify. There's another parameter called bandwidth multiplier. This is actually used by Ruby's simple network model, not Garnet. Simple network is the Ruby's base network model, which is just a fuzzy network, connects things. The routers are not modeled in a lot of detail. To set link bandwidth in Garnet, you have to actually just set the flit size that I'll talk about later. Okay, so these are some of the default topologies we support right now. There's a point-to-point, there's a crossbar. The mesh has these 3 variants, and I'll again talk about this from the routing point of view. The dire corners is the one where there's just 4 directories. The others just connect directories to every node. And then there's also cluster topology that's often used for modeling more CPU, GPU systems. Okay, so now that I have the topology, how do I route, right? How do I decide how to go from one node to the other? So by default, because the topology can be generic, Ruby has routing tables that get created. So the idea is once you specify this topology in Python, these routing tables will automatically decide shortest path routes for you. And you can bias this by adding weights. So if I have 2 paths that have the same distance, I will try and choose a path that has lower weights over higher weights. So that's why weights are used, and you can play tricks with weights to actually implement more complex routing algorithms. But this is still deterministic. Like at design, once you specify this, unless you have 2 paths with the same weight, in which case you can randomly choose between them, you have specified a topology, that's a routing algorithm that's deterministic. It's not adapting based on traffic conditions. If you want to implement something that's more adaptive, you will have to dig into the Garnet code and maybe do it there. You can't do it from the topology file. But this essentially lets you kind of decouple all of those details and just specify a topology and get it to work. So the reason weights are important is because of deadlocks. So again, a very quick primer. So you have what are known as routing deadlocks in networks, and that's a classic case where I have an update message. Yeah. So this is the classic case of a deadlock. Essentially, I want to use the buffer at the next router, but that's occupied. I'm waiting for, that to get free, but that buffer is dependent on another one, and so on, and there's a cyclic dependence. And so this is basically a deadlock condition because every packet wants to use the buffer at the next router. It's waiting for that to become free, and there's a cyclic dependence, right? So the classic way of avoiding network deadlocks is to make sure that you never get into this deadlock scenario. So if I have a routing algorithm that can, take any turn, I can potentially form cyclic dependencies. So if I can disable certain turns, I can make sure there's no deadlock. So the XY routing algorithm is a classic example. It says that you can never take turns that go from Y to X. Or the west first says you can never go from, south to west or north to west. So as long as at least 2 of these turns are disabled, like 1 in each of these loops, you'll never run into a deadlock. So that's the classic thing. This, of course, only works for more regular topologies. So this is the XY routing algorithm. This is the most popular routing algorithm for meshes. So it just says, I just use XY. So let's see how we actually model this with our topology file, and that's where those weights come in. So what we do is when we create the topology, and that's the mesh XY topology file, all of the X links have weights of 1, and the Y links have weights of 2. So what that means is, given a choice, I will always choose the X link if I can, and I will only choose the Y link when I can no longer use the X link because I have to make a turn, and that's the shortest path. So that's how you essentially implement XY routing, just by playing around with the weights. This is west first. So west first is slightly more, it gives you more path diversity because it says that, for these blue and green flows, I can actually use either of those paths. But for the orange one, I can only use this one because that's the destination is on the west side. So I always have to go west first and then make turns. So it gives more path diversity. And again, how I implement this in the topology file is I say that all the west links have weights of 1, all of the other links have weights of 2. Right? So given a choice between west and something else, I'll always choose that. Given a choice between the others, the code will randomly choose one or the other. So again, it's just random. It won't do it based on any other specification. If you wanted to do it based on network conditions and so on, you would actually have to go into the router code. This is something you can specify just from the topology side. Okay, so that's routing. So we've defined the topology and we've decided the routes. So this is something that works in general with any network model. Even if you use the simple network model in Ruby, this would work. Where Garnet comes in is it has more details for the exact flow control, like what goes what cycle. So it's a cycle accurate network model. So we have virtual channels that we support. So the idea is from the protocol level, as Jason described, there's going to be certain virtual networks that will be required, and these are just protocol level requirements. So, I might have some networks, I might require separate buffers for requests versus responses, because otherwise that will lead to a deadlock, like a protocol level deadlock. So Garnet would, respect that, and there'll be separate set of virtual channels for requests, separate set of VCs for response. So this is the minimum number of VCs you require in your system. And within each virtual network, you can have one or more virtual channels. And this is again a terminology thing. For coherence designers, virtual networks and virtual channels are the same thing. As a network person, I'm using virtual networks to define what the protocol defines, while virtual channels are something that the network adds just for performance. I don't want to do head-of-line blocking and so on. So I won't go into VCs. That's a whole lecture in itself. But basically, the idea is that they're analogous to, lanes on a highway, right? I have right-only lanes, left-only lanes that make sure that I don't block people who are maybe going straight. So similarly here, you can have different VCs. In Garnet, only one packet can use a VC at a time, and you have VCs that are shallower and deeper. So if you're sending, let's say, just coherence control messages, let's say ACKs or just requests, you typically use just a flit to send them. They are shallower. And if you're actually sending cache lines, you can size them to be deeper. So you actually have the ability to size them separately based on your traffic type. And then you have credits between the VCs. This specifies whether or not a buffer is available. So if a buffer is available, I can go. Otherwise, I have to stall. So things like credit signaling and all make it very cycle accurate, because you know exactly the congestion situation every cycle. So now coming into the microarchitecture. So now that I've decided, flow control, how do I actually design the router? So this is what a classic router looks like. So all of this might be very dense in terms of content, but again, I would encourage people who are here and also people who would look at the slides later to go in and take a look in more detail. But I did want to talk about all of the aspects just so that you have an idea of the power of Garnet. So this is what a conventional router looks like. And again, without going into details, typically what happens is you have a flit that comes in. It first gets buffered in one of the virtual channels in the VNet. You perform routing to decide where it has to go. Then you select a virtual channel for the next router. Then you arbitrate for the switch. As I said, these are shared links. So this is where the flow control comes in. Who actually gets to use the switch port? Every cycle has to be arbitrated. Then you actually read it out, send it over a crossbar switch, and send it over to the next router. So this is a classic router. And there's been a lot of research over the years to make all of these stages very, very narrow so that you can do this very, very quickly in a cycle. And that's what Garnet 2.0 implements. It actually lets you do all of this within a cycle while still maintaining that cycle accuracy. So this is what the code looks like. All of these are actual files like router.cc, input, switch, allocator, output, and crossbar. So a preview of how the code works is you have the event queue of Gem5 that will wake up a router if there is some active packet that it has to process. And this will then call the wake up function in the input unit, which will read a flit and write it into the buffer, perform routing. This would then call the wake up function in the output unit, which would receive credits from the next router and update state. Then you call the wake up function in the switch allocator. This performs arbitration among these input buffers by making sure that only those VCs that have free VCs at the next router can actually go forward. So you have interaction between the switch allocator and output unit here. Then you actually select a VC for the next router, send a credit, read the flit out. And finally, you wake up the switch, which will then push the winning flits onto the link queue and schedule the output link wake up for the next cycle. So when I have schedule here, this actually means it puts this into the event queue so that next cycle the event queue can wake up these network links. And remember I mentioned you can model routers with different delays, and the way that is done is essentially if you wanted a multi-cycle router, you add delays in the flit saying that they're not ready to go in for switch allocation till a certain amount of time. So you still get that flexibility without actually having to model like a multi-stage one for these larger routers. Okay, so that's basically how all of the components are modeled inside Garnet. And now let's see, how this interfaces with the external system. So this is kind of a snapshot of where Garnet comes in, right? So you have the Ruby memory system, that's the coherence protocol. Jason alluded to message buffers. This is the interface between different buffers inside the Ruby memory system. So the coherence protocol will inject things into the message buffers, let's say an output queue, and say, I want to send this over to some node. And that's interfaces with the network interface inside Garnet. And inside Garnet network.cc, you have all of these objects. You have a bunch of network interfaces. You have all of the routers. You have all of the network links, credit links, and you have the ability to collect all of the network stats. And you can basically, this is pretty modular. You can keep changing all of these components. So now let's zoom into that network interface, because we've just talked about routers and links so far. So this is that topology I had described earlier. So at the topology level, this is what you define. But what Garnet actually does is it creates these network interfaces for each of these external links now. So these network interfaces are the ones that will translate the coherence messages into network packets. So essentially, this is where you specify a virtual network, you have the message, and what the network interface essentially does is it breaks the message into packets and packets into flits, depending on your flit sizes. And the message size decides the number of flits. So if it is a cache line, this would be maybe a 5 flit. Depending on the message size as well as the network flit size, you'll determine how many flits there are. And since this is C++ code, you can actually insert any any statistics or information you want into the flit. So oftentimes if we want to get some information about how many hops the flit took and so on, you can just add those as member variables. So anybody who wants to get more low-level details should essentially just modify that function, put more things into the flit, and you don't have to worry about other things. And when it's received, you can just get all of that data. So these are some of the configurable parameters. So you have the flit size. This, as I said, is the width of the links in the network. And this, in some sense, sets the bandwidth of each physical channel. The default size is 128 bits. So that translates to 1 flit for control messages, 5 flits for data. But this is configurable. You have number of VCs in each virtual network. So the total VCs actually becomes the number of virtual networks times the VCs per VNet. So this is something to remember. This is something that's right now, I would say, a slight limitation, where within each VNet you have the same number of VCs. But in principle, you may want more VCs in, let's say, a control VNet, less in data, and so on. And that's something that's not feasible right now, but not very hard to implement. Sorry. You have buffers per data VC and buffers per control VC. This is where I said you can have narrow, shallow, and deep VC. So you can set sizes for both. And you can specify whether the routing algorithm should be that custom, the default the default weight-based one or custom. And all of these are defined in this Python file here. So all parameters, again, this is just, Gem 5 101, all parameters are essentially defined in some configuration Python file, and you just have to change it there. You actually don't need to go into the C++ code if all you care about is changing parameters. And on that line, though, because there are a lot of Python files where things get changed, it often becomes a little confusing. So I just wanted to have a slide kind of explaining the flow. So you have all of these internal Python files with definitions and default values, right? Routers, links define the latencies, network has certain definitions, Garnet network defines flit size, and so on. And then you have, in the source code, you have the configs folder, where you again have a set of Python files. And these Python files actually let you override whatever is in those default files there. And anything that's in these config Python files can be specified from the command line. So if you wanted to run a simulation where you wanted to change things from the command line and not recompile Gem 5 every time, you should have that appear in one of the config files here. And that will let you run things. So oftentimes, for instance, if you want to run simulations with smaller and larger flit sizes, you can just do that here rather than having to change it there. So I would recommend changing things here rather than at the global level. So now how do you actually run Garnet? I'll just quickly give a brief overview. So you build a Ruby coherence protocol. So let's say we've built the Moisey Hammer protocol, and this determines the number of message classes or virtual networks required. And then all you have to do to invoke Garnet is just say, dash dash network equal to Garnet 2.0. If you don't do this, the default network is the Ruby simple network. And again, you can specify the topology. If you don't do that, the default topology is just crossbar. So you can see all of those defaults in those config files, but this is how you specify things. There is a way of running Garnet in a standalone mode, and I just wanted to briefly highlight that. So for this, you would build the Garnet standalone coherence protocol. This is a dummy protocol. This actually is not a real coherence protocol, but it lets you still have the same coherence interface with the rest of Ruby while completely controlling the traffic that's inside the network. So now you can run user-specified synthetic traffic. You can say, I want to run, let's say, uniform random traffic at a certain injection rate and so on. So this is all specified in this file here, this Garnet synthetic traffic, where you have a bunch of traffic patterns. It has a certain set of virtual networks, and you have the ability to control it completely. You can decide how many packets to inject, maybe to just inject from one source to one destination or one source to multiple destinations. So you can control everything, which is a great tool for debugging and also heavy customization and really stress testing your network. So these details are up on the wiki here. Finally, just like a snapshot of what the final outputs look like. So when I run a sample simulation like this, in the config file, you'll basically have information about the routers and the links. And if you see, you can see, what were the parameters that were set. You can see what routers the links connect to and so on. And you have the final stats file. So this system.ruby.network is what you care about for network level stats. And you have a bunch of stats per VNet. So essentially you have packet and flit stats per VNet and overall, and you can always add more stats from garnetnetwork.cc. And finally, in the slides, I have a set of FAQs that I've often received from the mailing list, or things that people care about. So I would encourage you to just go and take a look at this later in case you have questions on how do you get different things. And so there's things related to system level modeling, topology, routing, microarchitecture, and finally, I'll conclude. So as I said, this is an open source simulator. I would really encourage people to use it and contribute to it. Right now, I think actively the people who've been managing the code is myself and a lot of folks at AMD Research. And right now, Garnet, as I said, works only with Ruby, but it is a standalone network model, and there's no reason for it to not work with the classic memory system. It's just that nobody's, I guess, had the time to integrate it. So if somebody wants to do that, that will be great, and I would love to talk to you. And these are some more resources in case you have questions. So thanks.